So with this audience, it seems like I will learn more than I will be able to say anything. So hopefully I will learn much more than I will be able to teach. So let's pick some objects which I will be using. So G is a simple Lie algebra over complex numbers. Yeah, so my base field is going to be complex numbers. Although most of the results will work for any algebraically closed field of characteristic 0. So sigma will be a curve and this means that reduced but not necessarily connected. And now I will fix two numbers. Fix S. So this is number of markings, no, number of points on sigma. And also I will need C, which is central charge of the theory, which I will explain. So first definition. Actually, I will really need at some very soon reduced with at most nodal singularities. Okay, so by a S-pointed curve, we mean sigma algebra together with distinct points, distinct and smooth points. So P is in sigma. And I require them.
Oh, and they are numbered.
Say it again?
They are numbered.
Yes, they are numbered. That's right, indeed. Yes. So ordered points. So smooth ordered points. That's right. And I will require that, moreover, each irreducible component of sigma should have at least one yard. So I require that each irreducible component of sigma should have at least one yard. And this will ensure that sigma minus P, okay, I mean, this is little bit abuse of notation. So when I write sigma minus P, I mean, even though it's an ordered set, I just mean sigma minus P1 through this. So this will ensure that this is affine. And we will see that why do we need this assumption, because I need a good supply of functions on that. In any case, it will become clear in a minute, in few minutes. Okay. So the next object is Affine Lie algebra. Oh, this is the one. This also is right. So Affine Lie algebra. So this I will denote by G hat. And this is by definition G tensor C double bracket E together with a central charge, no, central element C. And the bracket H, I'm sure you all know that, but let me just write it all the same. So this is XY tensor FG plus, okay, so I will explain that. Let me write it, XY, and then residue and equals 0 of df times G. Okay, what is this? So here, this bracket is the normalized invariant form on G, so that if I take the highest root, theta, theta, this is 2 for the highest root.
Goat?
Second,
Do you mean goat?
no, I mean, no, I mean this. Now,
That's the linear form. That's not an element of the linear.
that's right. Okay. Oh. You are so right. Right. So that's right. So, yeah. So I can put code or what I would say that this usage of form on G star restricted to the Cartan star and theta is there. So let's just put it like that. So I want to make sure that this is equivalent to that. So this will be 2 theta, 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 2 theta, 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 theta is 2. So yes, yeah, that will be equivalent to that. That's right. Yes. Okay, so and C central.
But what is C?
So C is this element.
The element of what?
Okay, so G hat by definition is G tensor C, this Laurent series in T, together with one extra element, which will be a central element in this Lie algebra. Right? Yeah. Okay, so representations of G hat. That's the extent. So I will. Okay, so my plan for today is to give an overview of how one proves the Verlinde dimension formula. So what are the different pieces and how they piece together? So my idea today is not to give you all the details, but to give you an overview today. And the next lectures will be filling up all the details of various pieces of the thing. So, so representation of G. So we will be interested in integrable, highest weight modules, and I'm sure you all know these words, but in case you do not, I'm going to explain this next time. So let's just assume this in case you don't know. So classification. of such modules. So I have fixed a central charge, and that will play a role. So isomorphism passage. Of these integrable highest weight modules. So, okay, so I will just say integrable highest weight modules. So isomorphism classes of IHMs with central charge C. So central charge C means that so C acts by CV. Now C is a central element in the Lie algebra, and this is a highest weight integrable module. So first of all, it's already irreducible because it's integrable and highest weight. I mean, I will say something more about that next time. So it's already irreducible, but I just need highest weight module to conclude this, that CV is going to be for all V, yes, for all V in any such representation. Let's just call it H for all C in H. CV is going to be this constant. So that's called the central charge. So what I'm going to say that isomorphism classes of highest weight modules with central charge C are parameterized by this set DC. And let me write that. So this consists of all those lambda in H star. I will explain the notation in a minute. Such that lambda alpha I check is in Z plus, and lambda of theta check is at most C. Okay, so there are some notations here I need to explain. Okay, so first of all, though G, I am fixing a Borel subalgebra. And a Cartan subalgebra. So this is Borel subalgebra. This is Cartan subalgebra. So this set DC is by definition all those linear forms on the Cartan subalgebra. Side okay. So alpha I are the simple roots.
Is small c an integer?
Yes, that's right. That's right. Indeed, indeed. Yes. Yes. Actually, I can take a non-negative integer, but let me take a positive integer just to avoid certain it's a positive integer. I mean,
For 0, you would have just a trivial representation.
Exactly. That's right. That's right. Exactly. So there are some things which I might say might be not quite correct there. In any case, as you point out, it's trivial representation. Okay, so alpha I are the simple roots of G, not of G hat, of G. And alpha I check are the corresponding co-roots. Okay, so I think, and theta was already mentioned, theta check is the, okay, so here I have to be a little bit careful here. So theta check is not the highest co-root. It's the co-root corresponding to the highest root theta. Yes, so let me specify that. So theta check is the co-root for the highest root theta of G. So theta lives in H star, and this lives in the Cartan. Okay, so I think now I have explained at least whatever the notation is involved here. And the correspondence is any lambda goes to, and I am going to denote this representation by h lambda. Okay, now, really speaking, I should specify C here. So, okay, so this lambda corresponds to a integrable highest weight module with highest weight lambda. But keep in mind that this is for the affine Lie algebra. So once I specify the highest weight for the finite G and I specify the central charge, then it completely determines the representation. So since I am going to, throughout this course, I will fix C once and for all. I may not really denote HC lambda, I might just say H lambda. But let's keep in mind that I am going to work with a fixed C in the theory. And sometimes I will remember to put it there, and often I will not remember to put it there. Okay, so this lambda, so SC lambda is the, so this is the integrable. So this has highest, I will just write highest weight lambda and central charge C. This is the option. Okay, so now comes the fundamental object here, and that is called the space of conformal blocks and dual conformal blocks. So let's see. First, let me define the dual conformal blocks.
Sorry, Shrawan.
Yes, of course.
Remember what we got. Like, so sections of the determinant bundle of the affine gross mining, is that meant to be one of these, or?
Right.
Then what parameter would it have?
That's a little bit more delicate question.
Okay.
So, okay, if you are looking at SLN,
yeah,
then it will be C. No, okay. Right. So if you are looking for SLN like vector bundles or SLN bundles, and you take the okay, what do you mean by determinant bundle?
Oh, you have some lattices, I think of it inside that. And I think the quotient I take it in terms.
So, right. So determinant bundle, you raise it to power C.
Yeah.
That will correspond to this C.
But you seem to have, there are many different things, right? Where in this set,
yeah,
that corresponds to one element of your set D sub C. Is that right?
Wait a minute.
So if I take section,
right, exactly.
Am I right? Section,
you are absolutely
supposed to be giving you one of these.
You are absolutely right, and you are 100% right. And the point is that that will correspond to lambda to be 0.
Oh, okay.
See, because lambda could be 0.
Okay.
But this will correspond to a representation of highest weight 0, but central charge C. Okay. And that's a very non-trivial representation.
Okay.
So you are absolutely right. And I said that the question is a little bit more delicate. If you go out of SLL,
yes, okay,
then there is something called Timkin index, which will come to play in the picture, which I will explain at some point. Okay, so yes, so space of dual conformal block. So we have already this object, S pointed curve. So that's an object which we have fixed. And now to those points P, we associate lambda 1, lambda S, where each lambda I is in DC. Okay. So to these points P, so you should think of that this lambda 1 is attached to P1 and lambda S is attached to PS. So this is so I attach to each pi lambda I. And in fact, I mean, lambda I h, just I am attaching a representation there. So that's what I'm doing. Now, the space of dual conformal blocks, so this is definition now, a basic definition. So this is the space of dual conformal blocks. And that space, let me just set the notation. So this is V sigma, P and lambda. And this is by definition, you take H lambda 1, tensor H lambda S, and divide this by, and I will explain these, but let me just write first, and I will explain all this thing to this H lambda 1, H lambda S. Okay, I need to explain this notation. What do I mean by exactly this? So let's do that. Okay, right. So first of all, this each H lambda I is a representation for G hat. Something is bothering you?
No, it's going for.
Yeah, it's going. Okay. So each lambda I, H lambda I, is a representation for G hat. Same central charge. So the tensor product, so this gives us that H lambda 1 tensor H lambda S is a G hat module. But now, what is, first of all, what is this notation? So G sigma minus P is by definition, you take G tensor C of sigma minus P. So this is the affine coordinate frame. Now, see, now let's go back here. That's why I needed this restriction that each irreducible component of sigma should have at least one point pi. So this gives us a good supply of functions here. Okay, so this is a Lie algebra under the standard point-wise bracket, Lie algebra under, and there is no central charge here. So X tensor F, Y tensor G, is nothing but XY tensor FG. So X and Y are in G and FG are in sigma. No, not C, sigma minus P. Okay, now how does this act on this space? So I have to specify that. So, right. So let's take X tensor F acting on some element here, and I'm going to write it as V1 tensor PS. So here, Vi is in H of lambda I, and X tensor F is in G sigma minus P. Now this action is, okay, so X, no, so let's write V1 tensor in the Vi factor. I'm going to take X tensor FPI. I will explain this notation in a minute. Acting on Vi, PS. Here. Okay, so what did I do here? So we want to act this Lie algebra now, this Lie algebra on this module. So the action is I take this V1 tensor, so on Vs. So this is on the ith factor, I am using X tensor FPI. Now here, what is this? So one has to be a little bit careful about this, exactly what this is. So let's see, where should I go? Maybe I will. Oh, I still have one code, so I can use that. So FPI is the Laurent expansion F at Pi with respect to a local parameter. Let's say a fixed local parameter. At Pi. So what we are doing, and that's why I took my points Pi to be smooth points. So Pi are smooth points, so I can choose a local parameter, which I'm just denoting by Ti. And FPI is the Laurent expansion of F at Pi. And now once we have that, then this belongs to the Affine Lie algebra, and we have to turn free. But keep in mind that the Affine Lie algebra had a central charge, and the bracket was not just this part, but there was this contribution. So now there is a little lemma is that H lambda 1 tensor H lambda S is indeed a module for the Lie algebra, G tensor sigma minus P because of the residue formula. Now one should be a little bit, I should mention two things here. First of all, this requires all the central charges to be the same. So if we had different central charges on these, it will not work. So that's why we need to take all the central charges to be the same. And usually, residue theorem is mentioned for smooth curves or smooth varieties. And I can just take the normalization of the curve and I can work there because the points Pi are all smooth points. So it does not affect the residue there. So it will be a very easy consequence of the residue theorem that this is indeed a Lie algebra action.
So you have to only need same charge in each irreducible component.
Say it again.
You only need same central charge in each
Exactly.
component.
Exactly. That's right. Exactly. That is true. Yeah, that is true. But you are absolutely right. But most interesting case is going to be smooth, and then we will apply your moduli and extend the results there. So yeah. Okay. So this is a Lie algebra action. And once it's a Lie algebra, it's a Lie algebra action, and this notation, where did it go? This one. So this one just means that you apply this one, and then take the image there and quotient it out like that. So is the definition clear?
One thing which confuses me a little is how much the local coordinate has been used.
You are ahead of me. so let me say, in fact, that was going to be the next theorem. So yes, so let's see, what should I erase now? So I'll write it here. Yeah.
Part of the theorem going to be that the higher homology groups there are zero? Like that's a zero at the moment.
Yes. You have a very good point. Let's see if I know an answer to that. Actually, I do not know an answer, but I can think about that and let you know. Yeah, but I don't know the answer. Okay. So theorem. So as Pierre already mentioned, so there are two parts to the theorem. Theorem one, that this is space V sigma P lambda up to a canonical isomorphism Okay, so anyway, I'm not going to explain too much, but probably I will give a proof of that next time. So up to a canonical isomorphism, canonical is okay. Canonical is only up to scalars. So V sigma P lambda up to a canonical isomorphism does not depend upon the local parameters. And the proof actually is not very difficult. But in any case, today I want to give you an overview of the whole thing. So I will not prove this today, but next time. And two, P sigma, P lambda is finite dimension. Okay, so once you have a finite dimensional vector, and this is called the space of dual conformal blocks. So
am I remembering right that if I inserted some more points with zeros on them, it wouldn't change the dimension?
Exactly. So you also are ahead of me.
I'm just trying to.
No, you are right. I'm coming to that. In fact, very soon I'm coming to that. Yes. So this is space is finite dimensional. So of course, when you encounter a finite dimensional vector space, somewhat canonically associated. So the first and most important question you want to ask, what is its dimension? So question, what is the dimension? Of V sigma. And this course is about solving this problem. So that's what I'm aiming at. So that's one aim of this course. And then connect this space with sections on the moduli space of G bundles. So that will be the second part of this course. So, right. So I will not write down the answer right now, but I will write down the answer at some point. So in any case, Verlinde, and I should specify this is Eric Verlinde, gave a formula, okay, gave a formula for its dimension. And in fact, he gave this formula while he was visiting this institute, 1988. So, I mean, this formula is like, I'll just say that this formula is like wild character formula or wild dimension. Actually, it's more like wild character formula. But I will not write down right now. But now let's look at the various pieces which go into its proof. That's what I want to do. Okay. So let me also define the space of dual conformal block, which is not so important, but maybe at some point I might need that. So let me define that.
So you also will not depend if you deform the curve keeping the nodes, nothing will
Yeah, exactly.
You already called that dual conformal.
Oh, right. So I'm going to define conformal block. So that is very similar to that. I can define in two different ways, which are clearly equivalent. So this is V sigma E lambda dual, just vector space dual. And this is also equivalent to, we take half of, let's see, and I will take H lambda 1, H lambda S. Clear, I mean, this is like, so that's that. Okay. So now let's look. Oh, actually, I'm supposed to give a short break. Oh, no, this is still not the time. Yes. So I'm going to now write down some of the theorems. And in fact, Venkatesh and Pierre have already said what those theorems are. So let me write, one. This is called propagation of moduli. So this is space. Okay, let me, So V sigma P lambda is isomorphic with V sigma P, and I'm going to attach one more point, and then I'm going to take lambda and 0. I will explain this notation in a minute. So where Q in sigma is a smooth point, distinct from P. And so we attach 0 to Q. So this space of dual conformal block is same as you can attach a distinct point, smooth point, but to that point you attach the weight 0, and these two spaces are canonically isomorphic.
Up to a factor.
Up to a constant factor. Always, exactly. Yes. Actually, even the definition of this is only defined up to a constant factor. So, because I am in the notation, I'm not fixing a local parameter, because change of local parameter will define this space only up to a constant factor. So,
but you could have defined the affine Lie using this local field
that is found.
The question is to define uniquely the representation.
Right, exactly. That's we can do that. Actually, you are absolutely right. We can define the representation of affine Lie algebra without the choice of parameter. We can definitely do that, but I did not do that way. But you are absolutely right. We can easily do that. Only thing, it makes things a little bit more little bit more abstract. So yeah, right, exactly. Okay, so right, so this is one theorem, and actually it has one other part which is useful. Right. There is one other part to this theorem which is basically a consequence. But let me write that. So theorem 1 part A, and there's a part B to this. And if I take, so let sigma be irreducible. Then this is space B sigma P lambda is isomorphic with, let me write C, although often I will not write C. And I will explain this notation in a minute. And this is minus Q. Okay, let's see. Okay, right. So what am I doing? Right. Okay, so let me explain this notation. So what one is saying that this is space is isomorphic with, you take this integrable highest weight module with highest weight 0 and central charge C, and tensored with V lambda. And what is V lambda? So V lambda is nothing but V of lambda 1 tensor V of lambda S, a G module, not a G hat module. So V of lambda by definition is, now see, lambda i's are highest weights for G also. So now I take the standard finite dimensional irreducible representations for G, take their tensor product. So this is the definition of V lambda. Now, how does this act here? So this acts here by okay, so 2H.
I'm gonna say I cannot read. Could you?
Okay, right. Okay, so I have to tell you how does this act here. So this acts by a tensor product on this space. So I have to tell you how it acts here and how it acts here. So let's do that. So maybe I will come here. That's actually I could have anyway. So the way, right. So action of G sigma minus P on this V of lambda. So let's again take V1 tensor Vs, except that now Vi's are in V of lambda in the finite dimensional representation. And I take an element here, X tensor F. And this will be again V1. On the ith factor, I just evaluate this F at Pi. So I take X tensor F of Pi, so that's a scalar now, act on Vi, and yes. See, F was a function here, but I am only, oh no, 1 minute. No, sorry, I'm sorry. Sorry. Okay, sorry. So this Q, okay, see, Q was a point distinct from P. I took a point Q which was distinct from all those points. Now, the point Q is supposed to be attached here. The point Q is supposed to be married this one. And now I'm taking, so this is the action now. So you see, F is regular at Pi. So I can evaluate F at Pi, it's a number, constant, X, this is acting on Vi, and then I add it up. So that's the action on the second piece. And X tensor F on the representation of C lambda is nothing but X tensor F. You take its Lorentz series expansion at Q. Again, you have to choose a parameter, local parameter there, but it's a smooth point. So this is now X tensor F in G. Actually, I'm just, sigma minus Q. And V is now in H G loop. Absolutely. Something not quite right.
Just
Oh, actually, maybe I should have. Okay, why not I write it here?
so for the account of V lambda, you will
V sigma V lambda is also isomorphic with HC0 tensored with V lambda, and you take covariance with respect to G of sigma minus Q. And now the action of G sigma minus Q is by the tensor product action. On the second factor, it acts like that. On the first factor, it acts like that.
So what is the relation of A between A and B?
Right. There is a relation. There is a relation. What you, yeah. So I have, okay. So there is a theorem which is over both of these statements. So I have not stated the theorem which will have both of these things as a consequence. So this is really a corollary, but this is what I really need.
But it's really sigma minus Q. You're not removing the points in P.
Right. So here I am not moving, not so far, but I will move at some point. But right now I'm just saying that you have some set of P, you add one more point, but you attach weight 0 to that point, you don't change the space. That's what I'm saying.
for the second statement, the H0 is put at Q, and that's what is.
So let's see the second statement is exactly here.
V lambda, it is by evaluation at the corresponding.
Exactly. That's exactly what I mean. I at least try to write here. Exactly. So these are the evaluation modules now. Something is still bothering you, Venkatesh?
Maybe what is V lambda? What is V lambda 1?
Okay, so you see, that's right. So see, lambda i's are, I guess, weights for G also. Right? So in fact, the way I chose, now it's gone off the board. So you see, what was the requirement for lambda I? It had the requirement that lambda I of alpha j check was in Z plus. And also we required that lambda I theta check was at most. So in particular, these are dominant weights, dominant integral weights for the finite dimensional algebra G as well.
Oh.
Right. So that's an important point to keep in mind. So the lambda I, because this satisfies this condition, so lambda i's are dominant integral weights for the finite dimensional G. In particular, they give rise to the corresponding finite dimensional representation. Now, this condition actually ensures that this is dominant weight for the affine Lie algebra. This condition just ensures that. So if I fix the central charge C, this ensures that.
I see.
Are you?
No, I'm
Are you okay now?
Yeah.
Okay, so where are we? Right. So no, Venkatesh, you are absolutely right. This does not immediately follow from this, but there is a like an umbrella theorem, which will have both of these as immediate consequences. So I did not state the umbrella theorem, which I will do next time. But these are the consequences which we will need later on. Okay. Right. So this is 50, no. Yeah. This is 50 minutes. When do you want to break for 10 minutes? Or, I mean, I can keep
a logical place then.
Say again?
At a logical start for you and.
Okay.
long after.
Actually, next thing what I'm going to do is the factorization theorem. I have to state that. So we can break now if you want to have a 10-minute break. Yeah. So let's do that. So the next thing I'm going to do the factorization theorem, and then I will say how things differ when you do the deformation. So that's what I'm going to do. So right. Okay, so let's see what do I mean. So this was the propagation of vector. Right. Now I say the factorization theorem. So that's okay. So the setting is the following. So let sigma p has a node Q. Now, of course, Q will have to be different from PI because PI are smooth points. And I am not saying that that's the only node. It may have other nodes. I don't care, but it has one node Q. And now let's normalize sigma at Q. And since it's a node, I will get 2 points over this. So I start with a nodal curve with Q as the node, as a node, but I don't care about other nodes. Right now, I'm just focusing on one single node. And then I normalize that curve and I get the 2 points over that point. Okay. Now, so theorem now, let me state that. So there is a explicit map which and right. So let me write first, and then I will explain all the notation. So this is P, and then Q prime and Q double prime. Then I attach, and then here mu star, and let me write first, and I'll explain all the notation. Okay, right. And right now I think I have all the notation. Yes. So let's look at the term. So this is space, the original space of dual conformal block is isomorphic with, now I go to this normalized curve. I mean normalized at this point curve. Now I have this P, and I have added 2 more smooth points now to sigma hat. So I take this one, so that's the based curve sigma hat. And now so P hat or P vector had this lambda vector attached to them. But now at the point Q prime, I do mu star. And here I take mu, where mu runs over DC. And what is mu star? So mu star is nothing but V of mu star is nothing but V of mu star. So mu star is the, okay, so
position in evolution.
Exactly. That's right. So this is exactly this. So mu star is just the highest weight for the dual representation. And this is only for G, not for G. Yes.
So is this statement something that you would have to think about the global geometry of the curve to say, or is it something that's really about what's going on?
This is about what's going on here. This is what, so see, when you are normalizing it, So you are changing the genus. Okay. So how it's going to be used, I will tell you. So you want to prove the dimension of this space for a genus G curve. So sigma is a genus G curve. Let's take a smooth and irreducible so that so we start with a genus G curve and we want to prove a dimension formula for that. Now, so what we are going to do, as Darlene already said, you deform the curve, you create a node, you are not changing the genus, right? But now you normalize the curve and you are going to get a genus G minus 1 curve. So you wanted to calculate the dimension of this space, which is a calculation on a genus G curve. But here you are calculating the same thing on a genus G minus 1 curve. But what happened that you pay the cost by adding 2 more points. Right? So you keep going. And once you come to genus 0 curve, you will still you are still able to apply this factorization theorem, and the picture will be so what I'm going to do. So suppose I have 1 million points on P1 now. I created 1 million points on P1. So I will keep 2 points here. And I will leave 1 million minus 2 points on the other one. Okay. And I will create a node here, right? And then I will normalize. So now I'm going to get disjoint union of 2 P1s. Now I have got 3 points. And I have now 1 million minus 1 point here. And again, I keep on doing that. So eventually, you will have to do calculation only on P1 with 3 points. That's all you will have to do. And P1 with 3 points, the dimension of that space is controlled by this fusion product in the representation of Lie algebras, which I will come to in detail later on. So that's the strategy. So in fact, I've already told you in some sense the strategy. And you know, the algebra going from here to here, and then going to genus 0, and then going to 3 point. The whole algebra is very simple to really calculate very explicitly. And I will come to that very explicit formula. And then the problem reduces to P1 with 3 points, and there you have to do a little bit more work because it ties with the fusion product in the representation of finite dimensional Lie algebras. But you do something there, and then you get the formula. Okay, so that's this. And now,
So even here, both one constant floating around.
just a second.
You said when we're projective, here it's a little more painful.
Yeah, that is true. That is true. Yeah, that is true. That is true. Indeed, you are absolutely right.
We have a decomposition and direct sum, and each one corresponding up to a 5.
That is true. But what one will do that one will fix some local parameter here, and then the isomorphism is canonical. See, once we fix the local parameter, then the isomorphism is canonical. And that's what we are going to do. I mean, we will do the formulation in such a way that we are going to fix the parameter. Okay, so now comes the deformation theory here. Okay, let's see. I think I can erase that. Okay, so now we are going to talk about sheaf of dual conformal blocks. So we are going to sheafify the previous notion in fairly standard way. Probably it will be The formulation will be completely triggered to you all, but let me just specify that. So we are going to take pi sigma t over t. And so this is a family of S-pointed curves. So what does that mean? And okay, so this is, what does it mean? So I am going to take T an irreducible smooth variety. And so that's one. Now pi is a proper and flat family. Okay, so each scheme theoretic fiber of pi is a reduced but not necessarily irreducible, but not necessarily connected actually. Or with only nodal singularity. With only at most nodes. And what do I need? Yes, I sections here. Right. So pi mutually disjoint sections. Right. So okay, but I need that they should hit only smooth points. So and right. So sigma t 0 by definition sigma t minus this pi t union I from 1 to S to T is a smooth morphism. No, sorry. No, I don't mean that.
But the PI are into smooth locus.
That's right. No, right. Yeah, no. Yeah. So, how should I say? It's reduced PI mutually disjoint sections landing in smooth points. Okay, and actually, oh, that's right. Is an affine, sorry about this, is an affine moduli. And I require, so and pi is actually slightly stronger than pi is a smooth morphism in a neighborhood of union pi. That will take care of that. These are smooth points. Okay, so that is what is. So this tells us, so this will ensure that if I take any geometric point, then pi inverse t is a S-pointed curve as defined above. So now if I take the fiber over a geometric point, then the inverse image is a S-pointed curve. Okay, so now I can define the shape of conformal blocks. And maybe I will do it here. Okay. So shape of dual conformal blocks. So this is by definition. So now the notation is sigma t p r lambda. Okay, okay. So I should say that. So lambda is still does not vary with the points. So I'm fixing lambda to be one set of weights. They don't vary with the deformation. Okay. So the lambda are not varying with the deformation. So this is by definition, right? So let me write it and then I will explain this. And then I have to take actually, this is probably better notation.
Yes, enumerate, and I guess. Or HD means tensor O of T.
Yeah, exactly. That's right. So I just started the notation. So yeah, right. So maybe I'll just shorten the notation already here and then explain that. So HT of lambda is nothing but HT lambda 1, HT lambda S, where what is HT? HT of lambda I is nothing but you take structured shape of T and you take H of lambda I over numbers. So that's the shape. Here I take the tensor product, and of course the tensor product is over OT.
But I think you will need to have chosen a local parameter along each of the sections.
Right. Yeah, I am glossing over that point. That's right. Actually, I should mention that. You are absolutely right. Okay, so give me a minute. Let me complete the definition and I will come to that. Actually, I should have mentioned that. Right. So what is GFT? So GFT is nothing but G tensor, affine coordinate ring of something removed. So I wrote it there. So I have this one, sigma T0. So I take G of FT, a G tensor, C of sigma T0, affine coordinate ring of that.
You mean a direct image from sigma to T of O?
Yes. Let's see what do I mean by that. What the notation sigma T0? Right. So this is still an OT module, and I pick that. And now the action here is the same action as previous. So here I should just say that GFT dot HT lambda is nothing but the image of GFT tensored with HT lambda. to HT. Just take the action there. Now, as here pointed out, I should include a local parameter. So let me do that. Yes. Yeah, I should have done that before, but let's. Okay, so we choose formal local parameters. I will say Ti along Ti. What does this mean? It means that Ti is an element in the completed ring, sigma T, such that this is isomorphic with O. So that's so we need to choose a formal local parameter Ti along Pit, and this is what it means to say formal local parameter. Now, so what I'm going to consider all the while, so this has, so I will call it, so sheaf of sheaf of conformal blocks. Yes, with local parameters. Okay, so actually at such a deformation also, I will, what do I call it?
No, will you claim it is a locally free field?
Exactly. That is what one is going to prove. And we are going to construct a connection on that, on this coherent sheet. We are going to construct a connection, projective connection. We are going to construct a projective connection that will give us freeness. And yeah.
For a connection to give you freeness, you first would need it to know it is coherent.
It is, right. Absolutely. So exactly, you are several steps ahead of me. So actually, I wanted to give this thing some name, which I forget what do I call it. So if you, let me just say, it is such a deformation is called deformation with local parameters. Yeah.
It has a connection or a logarithmic connection with respect to the.
It's a connection on the smooth part, which extends to a logarithmic connection on the boundary. So if yeah, exactly. So it's an honest projective connection on the smooth part of the moduli space, but it does extend as a logarithmic connection on the boundary. Yes. Okay. So no, I was just trying to remember what I called. So this is called sheaf. Sorry. Deformation of curves with local parameters. So this whole thing which I defined with several of these properties, I'm going to just say these are deformation of curves with local parameters. That's what I'm going to call. Okay. And I'm assuming here T to be smooth, but that's a kind of a that's a series. Okay. Right. So So as Pierre pointed out, actually, I would not even call it a theorem. And that is that this one, V sigma T, P lambda, is a OD coherent sheaf. Now, the proof of this is very similar to the proof, which I have not given the proof so far, that this space of dual conformal block is finite dimensional. And the proof is really a kind of a simplified version of that proof. So in any case, I have not given the proof. Now, yes. Okay, so theorem. And let me see. So theorem. So the assumption is that assume so let sigma T be a deformation of curves with local parameters. Assume further that sigma T is, no, pi is a smooth morphism. So in particular, sigma T is smooth and all the fibers are smooth. Then this is space of conformal, this coherent sheaf V of sigma T, P lambda admits it is locally free and admits a projective flat connection. So that's an important theorem. Actually,
Something smooth, a little strong for that.
Let me correct that. Flight projective. I mean, I don't know if it makes a difference. Sorry, what did you say?
Is there something smooth, a little strong for the application? You want just to keep the nose that there.
Exactly. So that's right. So that's you're absolutely right. We need that, but somehow I'm going to circumvent that. This will be more or less enough for our purposes, but we will move to the boundary by some other consideration. I mean, we can extend the connection also as a logarithmic connection on the boundary, but that's one way to do that, but I'm going to do it slightly different way. Still prove that a bundle of conformal block, even if it's not smooth, is actually locally free without giving the connection. Of course, there is no connection there, only logarithmic connection, but I'm going to circumvent that. So there are two parallel ways to handle the same thing, but I'm going to take the other route. Okay, so this is now, so this is another important theorem. Okay, so right, so now let me write a corollary of this. Corollary So let sigma p be a smooth irreducible curve of genus G. Then dimension of this conformal block sigma p lambda only depends upon G and lambda. So as a corollary of this theorem, we get that if you have a smooth and irreducible curve of any genus G, then this dimension only depends upon G and the choice of the weights. So let's call this dimension notation that this dimension, let's call it F G lambda. Okay. So now so actually I have to extend this theorem. Okay, so far this corollary follows from here, but as we are already pointed out that we will need to do the deformation to a singular curve, to a curve with node. So we will require the extension of this theorem. So let's that V of sigma t p lambda admits is a locally free sheaf locally free O2 sheaf even without the smoothness assumption. And actually what we will really need that this should we allow one node in the fiber, but in any case there is this theorem that this is this. Okay.
I still have a question. If you have a family of curves with node, but if you have the number of nodes remaining constant, so the geometry does not fail, then will you have a connection also?
So you are saying that the number of nodes, let's say that is constant.
Yes. But you don't have this range of geometry. Which...
Right.
Isn't that contained in the statement that there's a logarithmic connection?
I don't see that.
I don't see so.
Yeah, I don't see that. Okay, that's a very good question, but I do not know an answer offhand. At least the proof which I have in my mind is indeed requires smoothness assumption on pi, but whether it can be extended to allow same number of nodes with the fiber, I will have to look into that. Yeah. Okay. So actually I have 10 more minutes. So let me write down now. Actually it's a corollary. So this number, so for any G bigger than equal to 1, So Fg of lambda is same as f of g minus 1 lambda mu star mu in C. So we get this corollary. So this is a corollary of the last theorem. Well, I should remember corollary. The above theorem and the factorization theorem. Imply. Okay, so now I can keep going. So this gets F0 of lambda and mu1 star mu1, mu2 star mu2, and so on, and mu g star mu g. That's what we get. So Fg is this one. And now again, if I use the factorization theorem, actually, right. There is one condition I have marked that g minus 2 plus f should be at least non-negative. Yes. So actually, here, okay. So for this, no. So far this is completely correct statement. Right. But now if I use the factorization theorem again, so again using the factorization theorem, we get. So what we can do now that this number can be broken into sorry. I have to put mu g in here. So I can break this into 3 terms. So actually now I don't know how to put the notation. So I'll just say delta 1, delta 2, delta 3. And at the same time. So and in the end, you might end up.
Many ways of doing it.
What's again? There are many ways to do that. That's right. Of course, there are many ways to do that. But let me just say what the underlying geometry, which I already said that. So I have all these points. And now I'm going to take 2 of those points here and rest points here. Now this is still a smooth P1, and this is still a smooth P1, but now I'm going to create a node, and then I'm going to apply the factorization theorem. But I will keep 2 points here, and I created a node here and rest point here, and then I keep on breaking this. So this becomes a disjoint union. Now the space of conformal block for the disjoint union is just the product, tensor product. So the dimensions just multiply. So here the dimension just multiply. So as we already said, that this can be broken into many different ways. But the point is that you only need to consider P1 with 3 points. Now you might wonder, and rightly so, that what if I only took 1 point here and rest on the other? So I will end up only in 2 points. But you see, there is a condition here because, so the condition is 2g minus 2 plus s. So that's the condition. Actually, I want to be completely accurate here. The condition is that will ensure that the Lie-Mumford type is connected. Does that sound right?
You don't allow consecutive lines with just 1 point.
Yeah.
That's not allowed.
Right. I think if the genus is 1 at least, because S is at least 1. So this is okay. But no, it should be at least. Sorry. So if genus is 0, then at least I should have 3 points. So that's why I need these 3 points. So let's make sure that I'm saying it correctly. 2g minus 2. Yes, no, I wrote it correctly. 2g minus 2 plus s has to be positive. And that comes from some connectedness assumption. Does that sound right? So I need.
No, I think that if you have only 1 point, you get nothing, but will it be false?
Okay. Yes, right. Let me think about that. So if you have 1 point, you are not changing anything. Right, exactly. Oh, absolutely. So right. So if we have 1 point, but then you are creating 1 point. So you still end up with the same number of points. Exactly. That's right. So that's right. Exactly. So if we have only 1 point, then since we have to create 1 more point here, we are not changing the number of points. So you can't do the reduction. Right. That's right. But also, in some of the proof, I will need, I forget now exactly where I need the condition, this condition. And this has something to do with the, so see, the generalization of your moduli, where we take the S-pointed moduli of curves. I mean, moduli of S-pointed curves.
Yeah. We want 3 points at least in
That's right. Exactly. That's right. So in any case, so that reduces the problem to this one. And that is encoded in what is called this fusion product in the representation. So actually, my time is almost up. So this is the kind of a overview of how the proof really runs. And the algebra here, even though it might look a little bit daunting on the first sight, that you have to do all this, you have to add these million points, and then you have to make a choice here. But the algebra actually is very simple. So I will explain that in good detail here. So I think I will stop here, unless anybody has any question.
So Sam, you have many ways of doing it. So it's a lot of identity. Those identities.
Yes, that is true. That is definitely true. That it gives lots of identities. Yes, you are absolutely right. But I don't know what. No, you are absolutely right that it gives lots of identities. But I don't know if it has been really exploited to get anything.
But I don't know, so there's some sort of fusion product which has an associativity, right?
Of course.
The same structure is still.
That's right. So I think the associativity will probably. Yes, exactly. I think you're right. I think it's the associativity. What you are saying is it just gives the associativity. And conversely. So right. That's right. Exactly. Yeah.
And next week you'll talk about representations.
That's right. So I will start with the definition of affine Lie algebra, not a very detailed one, but I will say exactly how they are constructed. And then I will start to fill various pieces. For example, finite dimensionality of dual conformal block. And then talk about how it does not depend upon the choice of the local parameter up to a scalar. And then what are the main idea of the propagation theorem. I will not give the whole proof because I mean the proof can be boring calculation, but at least I will give you the main ideas of the proof. And similarly for the factorization theorem. And the connection. So I will give the main ideas of how the proof goes. So we are meeting on Thursday, same time, 10:15 to 12. And there will be some, I think there is 1 week in October and 1 week in November where there will be no class. So. And maybe if you don't mind, if you can give me your email so that if I communicate anything, then I can just send you email to everyone at the same time. So, I mean, I know yours, but, but still you can. And if anybody wants exercises, I can give some exercises too.
Let's thank Shrawan before we go.
Oh, no.